This is you, and that is a world many light years away. Being a curious person, you wonder what that world might be made of, and how could you ever tell? Perhaps you could send spacecrafts there, land and investigate. But that is always the most prohibitively expensive means, if not impossible due to practical considerations. So how would you solve this puzzle? How could you ever tell what that world is made of? How did we solve this puzzle? Well, instead of just rambling the facts at you, I've decided to share a bit of the history with you, which will hopefully help you witness and understand the beauty of how we cracked this code. Let's get started. In the 1600s, the English physicist Sir Isaac Newton stumbled on a very counterintuitive property of light. It was known that sunlight passing through a glass prism somehow splits into the colors of the rainbow. Many at the time thought the prism itself was adding impurities to the pure white light of the sun to make those colors. Newton devised a series of experiments, suspecting that the prism didn't add any color, but sunlight was actually made of those colors. Here's a similar setup with 3 prisms and a lens. Drawn and animated to the best of my ability, that is. With a setup like this, Newton showed that after a prism split and dispersed the white light into the rainbow, it's possible to focus all the rays again with a convex lens and pass through a second prism. What we observe is that the light leaving the second prism is white, showing that those colors can be combined to recreate the white light. When this white light is further allowed to go through another prism, once again it splits into the spectrum of colors. Thus not only proving that white light is made of the spectrum of the other colors we've seen, but also proving that it's not the prisms that's adding in the color. To conclusively prove it, one can simply block some of the colors in the same experimental setup. When we do that, we see that only the colors we don't block show up in the rest of the steps in the light's journey from right to left. As you can see in the crude animation, the prisms and the lens the light is traveling through are not actually adding in any color of their own. Now, since Newton's days, we learned a few more very clever things about how light actually works. These new insights helped us take on the seemingly impossible challenge of figuring out what distant worlds are made of without ever stepping a foot there. In the late 1600s, Christiaan Huygens already got the ball rolling by framing light as a wave. And like waves, it had attributes like a frequency and a wavelength. In fact, there's a whole range of wavelengths of light that together lets us see things. As this wave theory of light gained popularity by the 1800s, we learned that what we perceive as color are just different wavelengths of light. And then came the best and the most relevant part. Every element on the periodic table, or even combinations of those elements, absorbs some of these wavelengths, but not the others. Meaning, say I took the element sodium and shone white light on it. The sodium will always absorb some wavelengths of light, but not the others. It would reflect them. This is also true for other elements and even combinations of those elements. So if you looked at a graph of all the measured wavelengths for this sodium test, you'd see something like this. There'd be a very specific dip in the graph revealing which colors were absorbed. How does that help us, you ask? Well, the way that helps us is by letting us create a catalog of similar graphs for other materials. We basically test every element and chemical we can and create a cheat sheet in advance. But how do we actually use it though? Imagine it like this. There is a distant world, far, far away, orbiting a star. We can first point our telescope at the star to see what wavelength of light that star is pumping out. We know that the planet orbiting it is getting showered with those same wavelengths of light. Now we point our telescope at that world orbiting the star. This world, like that block of sodium we have seen before, will absorb some of those wavelengths and reflect others. We can then go on to create a graph for this pattern where we can see what was reflected and what got absorbed. Now, all we have to do is to look up in our cheat sheet what materials are known to have those exact same dips in their graphs. The moment you find that match, you, my friend, have solved the puzzle. Without ever visiting that faraway world, without ever even sending a probe or a lander to that world, you are now able to study the previously unknowable world. Now, of course, my presentation in this video intentionally simplified the details of how it all works. But the point of the video is not to replace physics classes, but to share the joy and wonder of such an incredible achievement of science. I don't know about you, but to me, this is one of the biggest breakthroughs ever. It also makes me feel hopeful that someday we might just solve other similar puzzles which today seem impossible. Are there any similar mysteries you can share with us today? Maybe consider leaving a comment for the community to enjoy. If you enjoy content like this, please consider supporting this channel. You can do so by liking, sharing this video, or subscribing to this channel. Please feel free to check out my other videos. This has been The Scientist. See you in the next video.